Hello and welcome. Welcome to this presentation where we are looking at topic 5 and we're going to design generalized functional observers for time delay system. And so we're going to look at part 1 of this topic. There will be a series of presentations on this topic. So firstly, we look at this particular time delay system. And this is the result of the decomposition of an unknown input of, um, of a time delay system with a constant time delay, which was from topic 4, part 1. In that particular decomposition, the unknown input is expressed in terms of a linear or generalized functional, which is a combination, a sum of the instantaneous stack vector x1 bar of t, which come from this reduced order time delay system, and it's a delay stack vector. So we call it a generalized functional. And when we address in this problem, we can consider it to be like a multiple functionals where we could have matrices F and FD of dimension m, where m can be bigger than 1. They are known constant matrices. And just for the sake of the notation, instead of calling it z of t, we call it z bar of t, just to be consistent with all the bar the notation in here. So the idea here is how do we estimate this generalized functional in one go, directly, asymptotically, ensuring that z bar hat of t converges asymptotically to z bar of t at time go to infinity. And this is about design generalized functional observer. It's a new kind of observer that we are talking about. Okay, so that came from the background in topic 4, chapter 4 in our book. Now, this is the development. So, and it's actually presented fully in chapter 13 in the book, in the new book. Now, what we're going to do is we say, okay, let's propose the estimation of that generalized functional, which we call z bar hat of t. Let it take the following structure. Now, when we look at this structure, we basically have this omega t here is of dimension m. And all of those unknown matrices, M, MD, and all of that, they are of appropriate dimension. So we're going to find them. We're going to ensure that they are found in such a way that the estimation of this generalized functional converges asymptotically to the true generalized functional. Now, this observer structure is a fairly general structure. When we look at it, it's actually contain y bar of t, which is the output measurement from this system. Okay. And it's also contain another delay output measurement y bar of t as well. And we have this term in here. This is called an observer with internal delay. When this term is 0, when we don't have it, then we call it an observer without internal delay. And we have extra terms in our observer structure. We have it multiple of the instantaneous, the delay output measurement, and also delay by 2 tau. And the rest of these parameters They are associated so that we can cancel out the terms in the output measurement in here. Okay, and that's does not cause any difficulty at all, as we can show later on. So we need to find ways to determine these matrices. They are of appropriate dimension, and we have to ensure that metric n and nd, which form an aerodynamical equation of an error time delay system. We need to ensure that asymptotic stable so that the error can converge to zero. And these matrices, we need to find them. Okay, so we will go into the details of how it can be done. And at this stage, we like to acknowledge that the way we approach this solution of this problem is an adaptation of a method that we developed earlier in this reference here. So what we're going to do is we say, okay, we're going to introduce an error vector. An error vector. An error vector, we see the difference between this estimation of this generalized functional. Now I call it vector because in here we deal with a general situation where we could have more than one generalized functional. In this particular decomposition, that one is only one, but the theory we develop here is for multiple generalized functionals. So what we say here is we define error vector, which is the difference between the two of them, and which is straightforward because we already proposed the structure for this estimation, which is that right hand side terms there. So we substitute in and we subtract the generalized functional, which is basically that two terms in there. And the terms in here corresponds to z hat bar z hat bar of t, which is the estimation. And when we have this kind of expression, we can always express this omega t in terms of the error vector and the rest of the terms there. That will be used for substitution later on when we derive the error dynamic equation. So we then say, okay, we introduce this error vector. What are we going to do next? We're going to look at the error dynamic equation. We see the differentiation of this error equation. So we take the differentiation of respect to time, and therefore this become omega dot, and that become my bar dot of t, and so on. That's where we get to this expression. And then it's just a matter of substitution, and after some tedious algebraic derivation where we can then using all the information about omega dot in here, as well as using that omega t, which is the one given in here, and then also the delay terms and so on. And then also take into account the expression for y bar dot of t, in which we can get it by taking the differentiation of this thing, and it become x bar 1 dot t, and where you can substitute this entire expression in there. So you know that that's how we go about obtaining an aerodynamic equation. And for the sake of simplicity in here, this is what we got. This is what we got. It looks fairly long, but when we actually examine it, it's basically in terms of this kind of dynamical error time delay system. And then there will be terms multiplied by the measurement yt minus tau, yt minus 2 tau. These are terms associated with the parameters in here. And when we substitute in these terms in there and all of that, we got those expressions up to here. And then we got the terms which are included in this brackets. That is a metric equation. And then another one, and then another one. So that's how we obtain the aerodynamic equation. And by the way, in this derivation, we define T tilde, omega tilde, and U tilde. They are related to the following expressions. So T tilde is related to G, which is an unknown matrix, and N, which is the metric associated with the omega dot, and M is another observer matrix, and so on. So now, how do we derive the existence conditions? Now, the existence condition is basically what do we do in order to ensure that the error goes to zero at time goes to infinity. So that means that we're going to look at the aerodynamic equation here, and then we say, okay, let's make everything in here equal to zero. Now, if everything here equal to zero, that's where we get this expression. And when we have this expression, that means that, oh, J can be obtained because all of these are, as long as M is known. So in other words, this expression allows us to determine J once we know M. And then what's the M and all of that, we discuss about later. So effectively, when we look at these matrices or these metric equations, one here, another one here, and another one here. If we let them all equal to zero, that means we're going to have three equations. And from there, that's exactly what is going on in here. Another one in here, make it equal to zero. From there, we can explicitly obtain JD in terms of this unknown metric M and MD. And then lastly, the other matrix is in terms of MD. So that tells us that when we look at this expression, and this expression, it tells us that we need to find M and MD. If we know them, we explicitly obtain JD, and JDD. So from the expression from here up to here, that is straightforward. And then we say, how about this metric equation? If it equal to zero, then that is gone. And the same here. If this one is zero, and so this one as well. So that's where we got the following conditions. The first thing is that equation is zero, which means that we have this metric equation. So let's go back to here and have a look at this. If that whole equation expression equal to zero, then we can move minus f I bar 1 onto the other side, onto the right hand side, and that's exactly where we get this matrix equation. Now in this matrix equation, we know f, we know I bar 1, we know c tilde 1, c tilde 1, and f. So out of this matrix equation, we don't know what is the metric n, what is the metric t tilde, and m. And the same thing apply to the other matrix equation. If we make that thing equal to that two terms, addition of that two terms, then we have this equation here also. And we call this equation number 3, this is equation number 1, and lastly, equation number 4. And of course, when we make all of these terms in here, all this is equal to 0, and we also make everything in here 0 because it's 0 multiplied by y and so on. That all 0. We left with this expression, which is the aerodynamic equation of the error system. And that's where we impose the following condition. We require that this aerodynamic is stable. In other words, if it's stable, so we are actually looking at the stability or the exponential stability of this aerometric equation, of this error vector equation, and we want to ensure that it's stable. And so it means that when we zoom into these three equations, we can see that there are a number of unknown matrices. And by the way, the approach we adopt is based on this reference here. Okay. So we see that N, ND, T tilde, M, W tilde, U tilde, and MD. So that's where we define a matrix X, we call it X. And this one containing all of these unknown matrices, they come from these three couple metric equations. How do we solve them in a sort of systematic way? The answer for that is it's pretty straightforward, by the way. So if we go into define this matrix X here, and of course we can work out the dimension of this matrix, which contain all the unknown parameters of the observer, which is the observer given in here. So we can work out its dimension, and that's what's specified in here. So this one had dimension m rows. So we got m rows all the way, and that's where we got m rows. And this one got m rows, m columns, m columns. So that's why we got two of them. And these matrices, T tilde, for example, T tilde is related to the number of columns related to the number of columns of matrix V, which is we specify in here, which is P minus 1. So together, there are 1, 2, 3, 4, 5. That's why we got 5 times P minus 1 altogether, those columns together with 2m columns. So that tells us the dimension of this unknown matrix X. Okay. Now, what we do is we're going to stack them all together. We form an augmented matrix equation. So we're going to say, okay, let's stack these three together. And because of this arrangement, so we can express these equations in this form where X is already specified in here. And this matrix here, whatever it's called, I don't know what's its name actually. So let's call it that one. And that is specified according to this arrangement here, this matrix here. And so when we look at this big matrix there, we have all these known matrices F, FD. FD is actually come into this expression in here. And then we got C tilde 1. So when we examine this matrix, we can see that it contains all of the matrices associated with the original system. A bar 1, 1, A bar D 1, 1, C tilde 1, F and FD. So when we go into there, we can see that this matrix is a known matrix. And it's up this dimension in here. Okay. So it's up a dimension of this many rows, which basically that bit there, and it has this many column, which is n minus 1 column, 1, 2, 3 of that. So it's relatively straightforward to express the three matrix equations into an augmented form, which is this very well-known form in the literature where we deal with design the functional observer. And then the other metric, we see the known metrics in here, which is actually a row matrix, is basically linked to F, I bar 1, FD, I bar D11, and FD, and all of that stuff. So this is an equation, and we want to find solutions, which is basically we want to know, can we solve for this unknown metric X? And the answer is yes, that's not a problem at all, because it's a well-known metric equation. If you want to get the if and only if, this is the if and only if condition. We require the rank of this big metric, which basically come from these matrices, that one and this one here. And so we require this rank condition to be satisfied. And that can be easily tested, if we got this big matrix, we know all the matrices in there, we should be able to check that fairly easily. Now, if it is satisfied, so it has to be satisfied, and if it's satisfied, then the general solution of that equation is given by equation 7. So that means that we will be able to obtain this unknown matrix where we got all these parameters in there, and it's expressed in terms of this generalized solution. And that's where you find it very commonly in all the works on functional observer. When we are solving this metric equation, if the condition is satisfied, which is this one here, and this is the if or only if condition, then the solution is given by the generalized inverse of this matrix. Okay, it's called the Moore-Penrose inverse. In other words, when we take it inverse and we multiply cells, should give us an identity matrix. And it's also in terms of another general expression. Sometimes that one might be 0, so we might just left with only this solution. But in some other time, the freedom in this matrix, when it has more columns, when it has more rows than columns, we might have a chance of having this matrix non-zero. And as a result, we can exploit the extra degree of freedom, and then we can use it to stabilize the error time delay system, which we're going to talk later on. So when we check this condition, and if it's satisfied, then we can realize a generalized solution for X. And then what we can do is we going to, by the way, the metric I here is of this dimension here. Okay. So what we do is we say, and the way it is there, it's basically has 2m plus 5 times p minus 1 columns. So they basically they are associated with all the columns in this matrix. So what we do is we say, let's express this identity in terms of the first column there, I mean the first sub-column there. I didn't define what it is, but that one there basically has m columns, and this is the next one. It got the next one m column. The reason for that is when we have it like that, then we can express explicitly the unknown matrix n in terms of n1 and a free matrix here time n2. Okay, because the general solution has this extra degree of freedom, so that allows us to express the solutions in terms of this freedom matrix here. And so The solution is that when we put it in this form, we obtain an aerodynamic equation. This is the aerodynamic equation once we satisfy this existent condition, if and only if existent condition, and we get the solution for it. And then we solve for the solution, and then we extract out from there matrix N and ND. Remember, matrix N consists of the first m columns of X and the next m columns and so on. That's where we use this identity expression in there, okay? But the bottom line is the aerodynamic equation can be expressed in this form, where N1 is known, N2 is known because it's come from the expression in here, and if we know the generalized inverse of that matrix, so it's known. So N2 is known, and similarly ND1 and then D2. So when we look at this aerodynamic equation, we can see that it is in terms of this free matrix here. And so the last hurdle that we want to ensure is when we design observer, when we go about determining all the parameters, we need to ensure that this aerodynamic equation is stable. And of course, if we don't have ND, that bit there is gone. We only have an aerodynamic equation with no time delay, and the only thing requirement is the pair N1 and N2 has to be detectable or observable in the case where we want to assign all the eigenvalues or the poles of the metric N. So this is the general situation where we look at the observer with an internal delay. And therefore, we need to do the stabilization. Yeah, stabilization. So we basically solving a stabilization or a stability analysis. If Z I equal to 0, then it becomes ensuring stability. Here, if N2 and ND2, they're not 0, then we solve the stabilization of this equation. And so basically what we do there, we find a metric Zi such that this is stable for a given time. And in our book, we refer to this in chapter 20, where we pick some existing results in the literature, where people extensively look at time delay stabilization. This is a fairly standard, easy problem to solve for the stabilization. And they use in linear metric inequalities and all of that stuff. So the idea there is to ensure the stability of this system, so that we can ensure the error converts to 0. That's basically the idea behind that. Okay, so once we can obtain or we can work out that a matrix ZA to ensure that this aerodynamic equation is stable, then we substitute back into this generalized solution. So this is no longer 0, but this is something that will ensure the stability of the aerodynamic equation. And as a result, we work out the entire solution or the unknown matrices. Yeah, so we get all the unknown matrices. And with that, we guarantee that the aerodynamic equation involving metric N and D is basically a stable system because we actually do the stabilization in here. Okay, and so once that's it done, we then extract out all those matrices from X. For instance, if I want to extract this matrix T tilde out of X, then by looking at the positioning of this, that will come from the columns, the block, which is basically, this is the first 2M. And then the next P minus 1 column would be belonging to T tilde. Okay? And so on. So once we got all those unknown, known matrices T tilde, W tilde, and U tilde, then it's just a matter of getting the rest of the the observer parameters, because from here, let's go back to this expression. If we know the tilde, and from our solution for x, we know n and m. That means that we know g. And the same thing for gd. We know w tilde. We already got solution for x, which basically give us n md and all of that. So we know gd and gdd. So you see that it is so systematic. It is so systematic. The way we go about determining all of these observer parameters, they are so systematic. And likewise, one we know m and md from x here, we should be able to get the rest of the parameters. And as a result, we complete the design. We complete it completely. That means that we will ensure that this functional, the estimation of this generalized functional, asymptotically converging to the true generalized functional. And of course, the rate of conversion is all depending on the stability or the exponential stability or the beta exponential stability of the time delay system. And that's complete the design. And remember, the way we are solving this problem is we are solving the estimation in one go. In one go, we estimate that directly. So we estimate this generalized functional directly. And this is the structure of the observer that we propose in here. It is general enough to demonstrate our design method. It's got multiple delays in the output measurement, and to systematically derive all the parameters, we adopted this approach. We consider an error vector, and then we take the differentiation of the error vector with respect to time, and then we arrive at an error dynamic equation, and then we make all the terms, all the equations in there equal to 0, and we arrive at existence conditions. So the systematic way of doing it. And then when we get to the existence condition, the key to solving the parameters, they are basically these equations 1, 2, 3, 4. We want to solve for these metric equations. We want to solve for these unknown matrices in such a way that this aerodynamic system is stable. You see, so that is our goal there. And to solve for these matrices, metric equations, they involve n and nd and so on. So we stuck them into this form, and then we say, look, the if and only if condition is here, and if it's satisfied, then we get the generalized solution. And from there, we can exploit the freedom of having this extra arbitrary matrix in there, as long as that one is non-zero. And if it's non-zero, we can then express the matrix n in terms of n1 and n2 and z. Okay, and so we get this aerodynamic equation, and so it becomes a stabilization problem. We want to ensure that the error goes to 0. And in order for the error goes to 0, we basically solve for the stabilization. We see the LMI approach is one possible way, or there are many other possible ways. Whatever way, whatever method, our objective is to ensure this aerodynamic equation stable, this time delay system stable. So we search for that. Now, in the case where this matrix in here is 0, then that means that we don't do the stabilization anymore because that basically useless in there. Even this freedom they are multiplied by zero matrix. We just simply have n1 only and nd1 only. That means that the solution X is basically only contain that first term. There are situations that happens, but as long as we can ensure that this error the time delay system would involve N1 and ND1 is stable, that is also okay because we can guarantee that the error um, equation goes to zero. I mean, the error goes to zero as long as it's stable. It would be nice to have it go to zero in a quicker time, and that where when that term there is non-zero, we can actually achieve that. All right, so that basically the approach we take, and then another thing that we can also like to mention in here is when this matrix is zero. Of course, it's a zero m by m matrix because nd is of dimension m by m. In this situation, when nd equal to zero, we call it an observer without internal delay. So when we go back, and that is, in fact, we'll ensure that if the error dynamic equation, if it involve n stable, then we can guarantee that observer works for all value of time, delay time. So when this situation is zero, we call an observer without internal delay. That's the terminology they use in the literature. Now, if that is the case, then we reduce the condition down to another condition because in that case we don't have ND in there anymore. So we have only 1, 2, 3, 4, 5, 6 unknown matrices in this equation. And when ND equal to zero, really what really happened in here is we basically remove this row from there. Okay. So that means that the matrix has a less number of rows in there. That means that it's actually making the conditions a little bit more conservative because as you know that the more rows we have, the more chance of that matrix become like full rank and so on. So when we consider this situation, then we only need to solve for 6 unknown matrices in the modified metric equation. So when we look at these 3 metric equation, we're going to get rid of ND in there. So we say that one is no longer available because we make it 0, so that's gone, that one is gone. So we left with 3 metric equations, which is equivalent to getting rid of that row block in there. And so we have this reduce if and only if condition where that matrix there is still the same as before, but this matrix would have reduced number of rows, and which is the one in here. And of course, if this condition is satisfied, then it will give us an error dynamic equation without time delay in there. So we left it with this bit only, and therefore if we can find stabilization, which is basically we require the pair N1 and N2 to be detectable. When it's detectable, it means that the eigenvalue is stable. But if it is observable, that means what we can always find a matrix ZA to place the poles or the eigenvalue of that matrix anywhere on the S-plane. And the good thing about the advantage about this structure is that the error dynamic equation is independent of the time delay. So that works for a wide range of time delay system. So it has its own advantage On the other hand, it's a bit more conservative condition. As a designer, we have to have all of that into our disposal so that we can pick and choose whichever appropriate type of observer, depending on the situation that we are facing. So that concludes the discussion on the design of a generalized functional observer to estimate a generalized functional of the following time delay system. And we consider uh, a general structure for it. And we also discuss the other alternative structure. And so we go into, and by the way, when we look at the condition, and we look at this matrix, it gives us the FD in there. See, FD is in there. So that addition of this additional delay term in the generalized functional, actually it appear in this condition, in this matrix here. Yeah, and it also appear in here and here as well. Now, in the next presentation, in the next video, we're going to take examples. We're going to consider numerical examples to demonstrate the significance of generalized functional observers. And as I mentioned in the previous talk, we're going to show that this generalized functional observer, to estimate this directly, has advantages. And if you recall from the previous talk, when we were trying to estimate uh, delay stack variable, we couldn't do it by first estimating its instantaneous variable, which is x bar 1, 2 of t. Remember that example? We had an unstable fixed pole in there. So if we use the idea that let's estimate x1 by t first and then delay it by tau, it didn't work because there was no way we could get a stable observer to estimate x bar 1 t. So if we couldn't do it, how can we delay it? But whereas with this generalized functional, we can. So that's what we're going to do in the next talk. It's going to be exciting. And there will be many more examples to show the advantage of estimating generalized functional in one go. And by the way, as I keep mentioning before, nobody actually talk about this problem. They only talk about estimating that. Because at the time there was no need to do that. There was no need to do that. Nobody would say, why do you do that? Why do you have to estimate this? And the reason for that now very clear in our book. When we do the decomposition of the unknown input, we actually came up with that. And there are many more generalized functionals. Not just that, there will be multiple delays in there. And so there's a need for estimate directly. And because nobody look at it, so nobody realize the significant potential of it. And that's what we do in this book. Okay. And that's it for this presentation. I hope. Thank you for watching. And please join me again in the next video, which is part 2 of topic 5. We will consider a numerical example, and then later on many more examples to demonstrate the significance of generalized functional observer. So thank you very much, and I hope to see you again in the next video. Bye bye.